welcome to our final project for feedback control systems. I'm Christopher Lignon.
I'm Raichi Sun.
I'm Joel Mendoza, and we will be doing our project on the UAV.
Given that we have chosen the UAV problem, our team was tasked with being able to create a control system that will control the height of our UAV. There are many applications from GoPros to carrying packages, and we will be looking at a mining system within this overall UAV problem. For our control goals and metrics, our team decided to look at 3 different types of specifications. This is due to all the research that we've done, and we found out that settling time, overshoot, and steady state error were the 3 components that mostly other companies look at when making a UAV. So settling time is particularly for stabilizing the UAV at a reasonable time. The overshoot is so that we don't have large displacements in height, and the steady state error is so that we can have minimal user input error when working with the UAV. The type of controller we initially proposed is a PD controller, which would have a block diagram like this, which we'll end up seeing later on in a few
To model our system, we came up with this free body diagram and this block diagram. The mass in the free body diagram represents the UAV with the rotor force pointed up and the gravitational force pointed down. The damper included represents air resistance. According to our research, we found that the mass is 10 kilograms about, and the damping ratio to be about 0.5. And the block diagram has an input of the gravitational force and the rotor force, while the output is the height. Using the transfer function we obtained earlier, we found the root locus plot for the transfer function. And as you can see, that there is one pole at the origin at s equals 0, which makes the transfer function unstable. And we further proved this by analyzing the root Hurwitz. You can see that the first column has a 0 in it, which means that it's spiral unstable.
In order to implement a proper design, we first looked at the step response of the closed loop system without a controller. So as you can see from the step response, the settling time is extremely large, it's over 200 seconds. The system also has very high oscillations, which would not be viable for a UAV. We would want to reduce the settling time, and we would want to reduce overshoot for this situation. So we ended up deciding to use a PD control. Our specifications would be settling time to be less than 4.6 seconds, overshoot to be less than 5%, and make sure to have a steady state error of less than or equal to 0. Since our group chose to use a PD controller, we found that our controller transfer function would be KP plus KDS, which we would then implement into our controller block diagram, which would be next to our original transfer function. If we close the loop, we then find the controller closed loop transfer function to be KDS plus KP over MS squared plus B plus KD times S plus KP. Using this, we can notice that our system is second order, as 2 is the exponent in front of S. Using that fact, and also using that our original specification of OS to be less than 5%, we can find that zeta is 0.7 using the OS versus zeta graph. We can then use the fact that our system is second order and solve for KP and KD initial values. Using T settling to be less than 4.6 seconds and zeta to be 0.7, we solve for omega n, as omega n is just the square root of KP. Omega n was found to be 1.4, therefore solving for KP, we found that KP was greater than or equal to 2.1. We can then use the fact that 2 zeta omega n is related to B plus KD. We solved for KD and we found KD to be greater than 1.5, which can then be validated plugging it back into this equation and finding that our zeta is equal to what we found. In order to further implement our system, we decided to make sure that our controller would create a stable system. We took a simple root Hurwitz test in which we took the denominator of our controller closed loop transfer function, and we used Ruth Hurwitz in order to prove the system would be biostable. As you can see, the left half column of this array is positive, therefore proving the system is stable. We then went on to prove steady state error and to show that steady state error would be 0. Since it is a type 1 system, as the original transfer function has an integrator, it will always equal 0. But in order to prove the derivation, we took the open loop system of our controller block diagram, in which we implemented it into the derivation of a type 1 system. We then used the final value theorem in order to prove that steady state error would equal 0. After verifying our system, we found that we were successful as all specifications were met. Our original overshoot was supposed to be less than 5%, which can be seen as met since our overshoot was calculated to be 3.18 based off of the step response graph, as well as our settling time was supposed to be less than 4.6 seconds, and we met that as it was 1.49 seconds, which can be seen here as well from this step response. Our steady state error was proved to be 0 using the final value theorem. Using this root locus closed loop system, we also saw that our system was stable as the only pole lied within the region that it was supposed to lie within. Our gain values were calculated to be 64.267 for KP and 121.19 for KD, which were greater than the values stated previously, therefore those were also valid. After iterating the model in Simulink, we realized that the step response matched, proving our results even more valid. As you can see, the step response from Simulink matched the step response as if when we ran it in command lines within MATLAB. We plugged in our KP, KD values, and then we took a step response of that, and they matched. The peak amplitude were both 1.03, the overshoot was 3.18, which was exact same, and the settling time was also 1.49, proving our specifications correct. In order to further analyze our system, we looked at the robustness of the system. We tried to find gain margin and phase margin. Gain margin is calculated where it crosses negative 180 in the phase diagram. Since it never crossed, it's infinity. Phase margin is calculated when it crosses 0 dB, which can be seen here at about 12.1 radians per second, which is also a crossover frequency. That difference is then found to be 87.7 degrees. Using phase margin and crossover frequency, we can then calculate time delay, which is 0.125 seconds. We then plug that into Simulink to prove our system stable, and it was
In conclusion, our system successfully regulated the height of the UAV with desired specs through the use of PD control. All specifications were met. We have a really low settling time, virtually no overshoot, and a steady state error of 0. Our control system is also stable, which makes it a great tool to increase the efficiency of delivery